The following exercise is exercise 15.8, which is the usual checking of assumptions. We have the following economy. We have a production set consisting of points in the space, the elements of which they all lie in this interval, dependent on the time. This is t. Okay, so this is the production set. It consists of sequences like this one, which lie, every element of which lies in this interval. Okay, we have a production set, so this is the technology. This is the consumption set, which is simpler, because the only requirement is that consumption in any period must be non-negative. Okay, and we have a preference system. Specifically, the utility of any consumption stream is given by the infimum of the consumption stream. So we look for the highest lower bound of the consumption stream. This is a special kind of preferences. So we need to check if this economy satisfies assumptions 15.1, 2, 3, 4, 5. So all the assumptions underlying the second welfare theorem. The exercise is quite long, and some of the parts are easy. For instance, checking if assumption 15.1 and 15.4 are satisfied is easy. These are the convexity assumptions. It's easy and it's trivial, so we don't need to pay any attention to them. So let's focus on the more difficult parts. Okay, so here we go. Assumption 15.2 is we can check it in the following way. Let's have x and x prime as two consumption streams in x in the consumption set, such that the following inequality holds regarding their utilities. It means, what does it mean? It means that this infimum is higher than this infimum. Okay, and we will use this fact. Let's have a parameter from this interval, and let's pick the sequence which is the weighted average of the two sequences. Both sequences, each sequence has a lower bound, and a highest lower bound, an infimum, which means that all t, this is true, right? Or in other words, the whole sequence cannot be lower than this infimum, and from this it follows that it is also true of this. It is also true in this form, and likewise, it is also true. Okay, so we know that this inequality holds. Okay, so we can say the following. It is a consequence of the previous line. All right. So if the question is the following, the utility of this sequence then we can say the following. This is the utility of this weighted average, which is the infimum of the sequence which we constructed as the weighted average of the two sequences, and we know that the infimum of the weighted average cannot be lower than the infimums of the sequences in the average separately, taken separately. And we can go on. We can take a huge step, but I suggest taking smaller steps, so let's slow down. Okay, this is also true. This is also true. And it is also true I am just expanding the expression. And given the fact that this is positive, it follows that it is greater than the utility of the series x prime. Okay, so assumption 15.2 holds. Next, please, assumption 15.3. The utility function is supposed to be continuous. This is tricky. This is a bit tricky. From the fact that the two consumption lines, two consumption streams are close to each other, we can call it epsilon over 2. And it is important, just one remark, continuity is related to the norm of the vector space we work with. So this is important. So from this fact, the fact that the two consumption streams lie close to each other, it must follow that the difference between the utilities of the two streams can be reduced to zero, to any small number. Okay, so let's suppose that the difference between the two consumption streams is very small. Okay, this will have some importance in the following. So we have two streams, x and x prime, which lie very close to each other all along. Both have a utility. Each has a utility. Okay, and suppose that this is smaller. Okay, now let's focus on this difference. This can be written in this way. Okay, which given the fact that this is smaller than any of the elements in the stream, it follows that it cannot be higher than this expression for all t. Okay, no matter what dynamics x and x prime have, we have a t. We have t such that is smaller than the infimum of the x prime series plus epsilon over 2, and to this t we have an xt element from the other series. So please note that we have two elements with the same index from both series, and we know that the difference between the two sequences cannot be higher than epsilon over 2. Okay, because this is what we established here. Okay, so they close. This is the reason why I emphasized a couple of minutes ago that both consumption streams lie very close to each other. So now we have the following. Okay, and it is the same as this is what we need. And this is the same as the following sum, which we receive by adding and subtracting the same element, the same number, and we can say that the following inequality also holds by dividing this sum into two parts in modulus. Okay, this distance cannot be higher than epsilon over 2, and this half of the sum can be treated in the following way. Given that xt prime is lower than infimum xs prime plus epsilon over 2, note, this is what we established here. It is also true it's elementary math, and we can squeeze this difference into the absolute brackets. So this half of the sum is also lower than epsilon over 2. So this is lower than this sum, which is epsilon. So given the fact epsilon is arbitrary, we are done. Sequence x and sequence x prime, the difference between the two, by reducing the difference between the two construction streams, where the distance is measured by the norm belonging to the space L infinity, the difference between ux and ux prime, the utilities, can arbitrarily be reduced. Okay, so I think this is a nice demonstration. So in sum, we can say that the utility function is continuous. Next, please, and the last part of the problem, because we skip assumption 15.4. So finally, let's have a look at assumption 15.5, sorry. We need to show that the set y has an interior point. Note, please, that set y is a sequence of intervals which are shorter and shorter. If t is 1, then it is supposed to lie between 0 and 2. If t goes to infinity, then y is supposed to lie between 0 and 1. So once again, set y is a sequence of closed intervals which are shorter and shorter. Okay, so let's have a sequence. 1/2 all along. This infinite sequence lies in the intervals, so it is an interior point. The problem is similar to exercise 15.7b. We are looking for a suitable sequence. We choose a positive epsilon and we complete the demonstration. So let's pick an epsilon from this interval. Okay, strictly lower than 1/2. Okay, please note that we don't need to show to any positive epsilon that we have an interior point. The only thing we need to show is that to to some really small epsilon numbers, so to any epsilon which is small enough, all the points in the neighborhood are interior points. So how should we do this? Let's pick another series Z which lies in the neighborhood of the series Y. What does it mean? This difference in the norm is supposed to be lower than epsilon. So the elements in the sequence Z, the difference between the elements of the sequence Z and the sequence X, this difference cannot be higher than epsilon. So to any sequence any sequence to which this difference is not higher than epsilon, any sequence lies in the epsilon ball around sequence Y. But these sequences are such that lie in the 0-1 interval. So to any Z, to any t, sorry, to any t and to any z, sequence z, all the elements lie in this interval for all t. And in consequence, the epsilon neighborhood around y is a subset of y. So we have chosen an appropriate sequence. This was y, consisting of 1/2 elements, 1/2, and we picked it was an important point of the demonstration. We picked an appropriate epsilon, and according to the norm, any sequence which lie in the epsilon neighborhood around the sequence y, the elements of this sequence, of this arbitrarily chosen sequence, cannot be greater than 1 and cannot be lower than 0. So to any sequence in this ball, they are going to lie in the 0-1 interval, so they lie in the production set. So we can find an interior point, and to any small epsilon number, sequences in the neighborhood are going to lie in this neighborhood, and they are going to be in the production set. So y is an interior point. This is the point. In exercise 15.7b, we need to show that the positive orthant of the space L infinity has interior points. This is what we are supposed to demonstrate. First of all, what is this space? What is the space L infinity? It contains infinite sequences that are bounded in this norm, in the subnorm. So these are infinite sequences, the elements of which are finite. This is a very interesting and important space. What does it mean if a space has an interior point? It means that we can find a point in the space, in this case, in the positive orthant of L infinity, which is an infinite sequence, in the epsilon environment of which, by picking an epsilon which is small enough, every sequence in this neighborhood lies in L infinity, in the positive orthant of L infinity. So simply put, we want to show that if we have a small enough epsilon, then all the sequences, all the points in this epsilon neighborhood, they'll all lie in the positive orthant of L infinity. So I think it's important to emphasize that we don't need to show that to any epsilon we have sequences in the positive orthant of the space. All we need to show is that to small enough epsilon numbers, all the points, all the sequences in the epsilon neighborhood of the point, all the sequences are in the positive orthant of L infinity. So if I wanted to sketch a figure, if this is point X, this is the N, this is the neighborhood, the epsilon neighborhood around point X. It's easy to draw a bigger environment around point X, and it's easy to find a point in this space, so in this environment, in this neighborhood, which lie outside the positive orthant of L infinity. So we need to pick carefully number epsilon. So this is the reason why we need to show that to small enough epsilon numbers, we all have points in the neighborhood that lie in the positive orthant of L infinity, in general, in the relevant space or set. So let's have the following sequence. This is a point in this space. And let's have epsilon from this interval. So now we are constraining the possible values for epsilon. If epsilon is in the neighborhood, in the epsilon neighborhood around X, then the difference between the 2 points cannot be the maximum difference between the 2 points cannot be higher than epsilon. It means that the elements of the two sequences, the differences between the elements of the two sequences are not greater than epsilon. So it means that to all n, oh no, the elements of the sequence lie in this interval. And given the fact that epsilon cannot be higher than 1, it also means that all the elements of the sequence lie in this interval, all n. So epsilon, y is in the positive orthant of the space L infinity. So X is an interior point. So lesson, this space L infinity, is much more exciting. And if we choose this space to be the production set, it will have an interior point, so assumption 15.5 holds. This is the lesson. Let's discover a further problem in the choice of a commodity space. We have already covered the fact that linear functionals on L infinity may not be in L1. It would be great if they were in L1, because any linear functional in that dual has an inner product representation, so we would have a price system. We can find a model. We will have an example. We can find a model in which theorem 15.4 works. So we have a linear functional that can be the basis for a competitive equilibrium, but this linear functional cannot be interpreted as a price system. So let's turn to page 460. This example is very instructive. We have an infinite horizon economy in which the commodity space is L infinity. In this economy, the solution is an infinite sequence. This sequence consists of time indexed quantities of the one and only commodity. We have production and consumption sets defined in this way, and we have the preferences. The preferences are important. You can see the preferences evaluate any consumption stream by the infimum of the sequence. So we evaluate any consumption stream by the highest lower bound for the sequence. And this is going to be a problem. By exercise 15.8, we know, we have already covered this exercise. By exercise 15.8, we know that the economy satisfies assumptions 15.1 up to 5. So we can rely on the working of the second welfare theorem. And the point is that we are going to realize that the linear functionals we have on the basis of the second welfare theorem cannot be interpreted as a price system. So the linear functional cannot lie in the space, in the dual space L1. Condition 2 and 3, which you can see in the middle of the slide, come from theorem 15.4, the second welfare theorem. So this is the linear functional, the existence of which is ensured by theorem 15.4 and especially by the 5 conditions underlying the second welfare theorem. So we can be sure that this linear functional exists, and we want to interpret this linear functional as a price system. So we want to find an inner product representation for this linear functional. We suppose that the linear functional has an inner product representation in this form. So we have a distinct price system. We have a price to each element in the infinite sequence. It cannot be identically zero because we can rely on theorem 15.4, and it claims that the linear functional is not identically zero. So at least for some time indices, it must be positive and or negative. Let's start with the negative case. If for any t we had negative prices, then the zero sequence had a higher would have a higher value, so it wouldn't work. So for some t, the price must be positive. Let's have another consumption stream, a price sequence, a good sequence that consists of ones. In this case, however, you can say that the value are the same for the two streams, because preferences are based on the highest lower bound for the sequences, and in both cases this highest lower bound is 1, so the utilities are the same for the two sequences, though the value by the linear functional would be higher for the x0 sequence, so it violates 2, because condition 2, under condition 2, if the utilities or the if the utilities of the two sequences are the same, then the values by the linear functional must also be must also be the same, so it violates 2. So the linear functional cannot be interpreted as a price system. It has no inner product representation. We can do some brain work to realize that condition 3 is not violated only if the linear functional puts all the weight to infinity, because the preferences are such that the preferences put all the weight to infinity, so we need a similar price system, but it is uninteresting, because as economists we are uninterested in preferences, and we are uninterested in price system that put all the weight to infinity. So what is the lesson? Even if we used L infinity as the commodity space, and even if it is most important, even if the two welfare theorems work, especially the second welfare theorem works, we have a candidate linear functional, but this linear functional has no inner product representation, because no matter how hard we tried, we didn't find any price sequence that would have been appropriate, so there is no inner product representation. So this is the result. This linear functional cannot lie in L1, because if it was in L1, it would have an inner product representation. So we have a way out, which we are going to discover soon in the next few slides. We can add additional requirements regarding the technology and the preferences, by which we can ensure that we are going to have a price system with an inner product representation. This is what we are going to do in turn. We are still looking for a solution to this problem. Let's try another space, the space of infinite sequences which are bounded in this discounted norm. In this case, we would need other preferences, as the one that we used previously is not continuous in this norm, but this is still a dead end, because with this norm we have no interior points in the positive octant. So we are still in trouble. There is a solution suggested by the textbook. We insist on L infinity as the commodity space, but we impose further assumptions on the preferences and the technology that ensure these assumptions, these additional assumptions ensure that we can construct another linear functional that puts no weight at infinity. Please remember, in the previous slide, we constructed a problem, an example, in which all the assumptions were satisfied. So there was a linear functional, but that linear functional didn't lie in L1, so it didn't have an inner product representation that could be interpreted as a price system, because the linear functional should have put all its weight to infinity. And given the fact that the necessary requirements were met only if the linear functional put all its weight to infinity, we were unable to interpret it as a price system. So with these additional assumptions, we can exclude linear functionals that put any weight at infinity, and hopefully under these additional assumptions, hopefully we can interpret the new linear functional as a price system. We need lemma 15.5 to make sure that the approach which we call truncation, so we want to make sure that truncation leads to linear functionals. So we have a linear functional ensured by the second welfare theorem and the remark. So we have a linear functional, but possibly it puts weight at infinity, and we want to exclude such linear functionals, but we want to ensure that the thing we have by truncation is still a linear functional, and lemma 15.5 ensures that this is a linear functional. The additional assumptions are assumption 15.6 and 7. With these assumptions, we introduce additional limitations on the preferences and the technology. Specifically, we ensure that the truncated sequences are still feasible and preferred. In exercise 15.11, we will see how to check if these additional assumptions are hold. And on this basis, theorem 15.6 ensures that there can be constructed a linear functional that doesn't put any weight at infinity, but it's still not a guarantee. Even if it can be interpreted as a competitive equilibrium under theorem 15.4 and its remark. And even if we know that we have a linear functional that puts no weight at infinity, so possibly it can be interpreted as an appropriate price system in the sense we need a price system, there is still no guarantee. In the next lecture, which is based on chapter 16, especially in exercise 16.6, we will see that even if all the necessary assumptions are hold, it is a separate step to show that there is a price system. So once again, theorem 15.6 only ensures the possibility of the existence of a linear functional that puts no weight at infinity. Please remember, once again, any linear functional that puts all its weight at infinity, like in the example in the previous slide, we are unable to interpret this linear functional as a price system. Theorem 15.6 is a step ahead, because under these additional assumptions we ensure that we can have a linear functional, we have a linear functional that puts no weight at infinity, but it is a further step to show that we actually have a price system. Exercise 16.6 in the next lecture is going to be very instructive, because there we will see that there may be a contradiction between the linear functional and the price system. So we will have a closer look at that exercise. The last exercise for the day is part B of exercise 15.11. This is very exciting. We will skip the opening parts of this exercise. So on the basis of the details, it's no big deal to show that assumption 15.7 is satisfied. But this is not the end of the story, because the solution manual contains a further inequality, which is very exciting and very useful, but it requires a separate demonstration. This inequality consists of two claims. First, the first claim, it exists, and the second claim, it holds. This inequality holds. First, let's try to show that these two claims are true. Then we will have some conclusions on the basis of this exercise. The limit exists if this equality, the lim sup between the lim sup and the limit infimum, holds. Towards the contradiction, let's assume that there is no equality. Let's assume for a contradiction that there is no equality. So the limit supremum is higher than the limit infimum. And if it is true, and we assume it is true, we can find an appropriate sequence as a consumption stream to which it holds. So its utility lies in between the limit supremum and the limit infimum, which are separate numbers, as we assumed. Let's have an index at which this truncation of the original series, the utility of the truncation of the original sequence, this inequality holds because of assumption 15.7 to any t above this limit, crucial threshold, it is true. Okay, which is a contradiction, with this inequality, especially this part. So the limit exists. Okay, so this limit exists. Now we can demonstrate that given the fact that the limit exists, we can demonstrate the inequality. For a contradiction, assume that this inequality holds, which cannot be true. Please note that this cannot be true because this limit in which xt is a truncation of the sequence x, this limit is ux. So this is a contradiction. So at the end of the day, this inequality holds. It means that the truncated version of a sequence cannot be lower. The utility of this sequence, the truncated sequence, cannot be lower than the utility of the original series, and it is very, very important because this inequality shows that it is rational for us to assume that when a sequence is preferred, its truncated version remains preferred because its utility cannot be lower than the utility of the original sequence. It means that the far end, if the far end of the original series has positive prices, then the consumer will choose the truncated sequence because it is cheaper. If the far end of the sequence has negative prices, then the consumer would prefer the entire sequence because in this case the producer would pay the consumer for consumption, but the producer wouldn't produce the products in the far end. So in one way or another, even if the far end of the sequence has positive or negative prices, it is rational for us to assume that the truncated version of a preferred sequence remains preferred. It is a very useful result. And finally, a short summary. Let's turn back to the example on page 461 because it was a very instructive example. We saw that preferences in that problem put the weight on commodities in the infinite future. So we needed a price system that also placed the weight on these commodities because in this case, conditions 2 and 3 would have been satisfied. But we don't like preferences that put huge weight on commodities in the infinite future because such preferences are not too realistic. But once preferences are such that commodities in the infinite future are simply unimportant, we want a price system that also disregards these commodities in the infinite future. So in this way, the price system and the preferences must be in line. So to solve that problem, we put some limitations on the preferences and the technology. So we had truncated sequences, and due to these assumptions, these truncated sequences remained feasible and preferred. And as we saw, in this case, we could construct a linear functional on the basis of the one that was ensured by theorem 15.4. And this linear functional put zero weight on commodities in the infinite future, just like preferences put zero weight on commodities in the infinite future. These commodities are simply unimportant. So if we can find a preference system with which a truncated sequence remain preferred, it's easy to realize that in these preferences, these commodities in the infinite future are simply unimportant. And once we don't need to pay any attention to commodities in the infinite future, why would we price them? Why would we need a price system that pays any attention to prices of commodities in the infinite future? So this was the solution to this problem. In the textbook, you can find an extension to this truncation technique. We covered in this lecture, we covered this solution in time. I mean, we had an infinite sequence and we truncated the sequence by disregarding the commodity stream in the far end. We can do this in models with uncertainty, so we can disregard, just like we disregarded commodities in the far end in time, we can disregard parts of a function that relates commodities to events with very, very small probabilities. So that was all for the day.